In this video, we are going to look at what causes the citric acid cycle to have a direction. Why does it run in the clockwise direction rather than the counterclockwise direction? This follows on with our last video where we looked at what were the actual reactions of the citric acid cycle, and then we'll couple into our next video where we're going to ask how does stuff get into the mitochondria in the first place. But today we're just focusing on that energetic question. Why does the citric acid cycle run in the clockwise, not the counterclockwise direction? Oops, wrong button. Okay, so what drives the citric acid cycle forward? Just a quick high-level reminder, the citric acid cycle is a catalyst that takes acetyl-CoAs, which have 2 carbons on them, and turns them into 2 carbon dioxides. This is an oxidation reaction. We are oxidizing those carbons. When we're oxidizing carbons from the acetyl to the carbon dioxide, we have to reduce something else. What are we doing? We are reducing NAD plus to NADH, and we are reducing ubiquinone to ubiquinol. And so we have this overall reaction that's generating carbon dioxide, reducing a bunch of NAD plus NQ. It does this over 8 steps. I don't want to belabor them, but I want to point out 2 features of this. The first is acetyl-CoA comes out here and spits out 2 carbon dioxides. The other feature that I want to point out is that there is a lot of NADH involved in these reactions, right? We're kicking off NADH as we do these oxidation reactions. And if you look at this, it's always drawn this way. It's a clockwise reaction. So we're going to follow that convention here. And we're going to ask today, why does it proceed clockwise, not counterclockwise? So the first thing we might look at is just the standard state free energies. So what I'm showing here are all of the standard state free energies for the reactions. And you can just add them up, right? If we say it's plus 5 here, minus 21 here, minus 33 here, et cetera, and we go through that in a counterclockwise direction, what we get is that the overall delta G naught prime is minus 51 kilojoules per mole. So this is a favorable process. What this means is if you could run it for an infinite amount of time without, worrying about energy barriers, this would happen. There's a problem though, and that is we've got one step in here that's actually very favorable going backwards. And if we think about a molecule that's wandering through this, right? It's going through the citric acid cycle, it's going to get here, and the odds of it jumping this direction are just really low. And so that might feel like it's a barrier. Why can't this reaction, or how can the citric acid cycle proceed despite this unfavorable step? And the way that it overcomes it is actually by allowing the reaction to equilibrate. So this is the standard state free energy. Recall the standard state free energy is the energy when we put everything at biological standard state, so 1 molar everything. So if we made everything have the same concentrations, this is saying that the reaction will start to move this way. We will equilibrate in this reaction. We start at 1 molar oxaloacetate, 1 molar malate. This is saying, oh, we're going to keep flowing in that direction. That means that the free energy, if we allow it to equilibrate a little bit, might not be the standard state free energy. We can access this using this formula we've talked about many times, where we can basically plug in the standard state free energy. And then these here are the concentrations of those different molecular components or those molecules in a cell or in a mitochondria. And so it turns out that's actually been measured, right? So this is the estimate of these concentrations measured in an E. coli cell, actually. So this is an aerobically growing organism that's an analog for our mitochondria. And you can plug in the numbers here and actually get out the free energy. So good chance to practice, actually. So if you want to pause and plug in numbers, practice doing this sort of calculation, go ahead and do so. I'll give you a chance. Go find your pause button. All right, I'm assuming you found your pause button. Great, let's plug in the answer. So if you plug in, the concentration of malate up here and the concentration of oxaloacetate here, et cetera, you get a number that is 6.5 kilojoules per mole. So it's still unfavorable. The reaction would still prefer to go backwards more often than forwards, but it's much, much less unfavorable than you would see. And if you convert this to betting odds, which is how I like thinking about free energies, it's only 1 to 15. So that means for every forward reaction, there are 15 backwards reactions. So, you imagine in a cell or a mitochondrium that's happening over and over and over and over and over again, you're going to eventually see things that actually go from the forward to reverse, going in the forward direction. Even though the majority of the reactions are backwards, you're going to see an appreciable amount of forward reactions. Okay. So let's start piecing together the whole citric acid cycle with this logic. What I'm showing here I'm going to populate is a graphic showing the citric acid cycle where the concentrations, the experimentally measured concentrations of all the molecules are shown as circles. So this is malate it's at 1.1 millimolar. This is oxaloacetate, which is at 0.004 millimolar. So I'm going to go back a slide, right? This is just those concentrations translated into areas. And the other thing I'm going to put on here are the betting odds, right? So this is saying it's 1 to 15 going forward. So that's what this is showing here. It's a 115 going forward. So this is actually a backwards reaction. It favors going backwards a little bit. All right, so let's start filling in the rest of the citric acid cycle using this notation. So we're going to add the reaction. It takes an acetyl-CoA and converts it into a CoA, taking that oxaloacetate and making it into citrate. And what we can see here is that this reaction is 245 to 1, favoring going forward. So this is a favorable reaction. Not a massively favorable one, but still favorable. We then think about the conversion of citrate to isocitrate. That's about 5 to 1 favorable. And then we hit the isocitrate to alpha ketoglutarate reaction. It's 2300 to 1 favorable. And recall that this is a step that kicks off a carbon dioxide and reduces an NADH plus to an NADH. The next step in the reaction is alpha ketoglutarate going to succinyl-CoA. That one is 1,000,000 to 1 favorable. This one also kicks off a carbon dioxide and does an NAD plus to NADH. So those are two very favorable reactions. The remainder of the reactions are about 1 to 1. They actually don't have a strong preference. The next one, succinyl-CoA to succinate, it's actually mildly favorable to go backwards, 1 to 15. Fumarate to succinate is actually also mildly favorable going backwards, 1 to 2. And then fumarate to malate is mildly favorable going forwards, it's 2 to 1. And so if you look at this, maybe pause for a second and think about it. What are some observations you make looking at the odds in the citric acid cycle? So pause, find your pause button. Right, you paused, came back. What I see is that you can basically draw a line through the citric acid cycle where the stuff up here is favorable and the stuff back here just doesn't really care. Another way we could put this is in terms of thermodynamics. The top reactions are out of equilibrium. They have an excess of reactants relative to products, whereas the reactions on this side are about at equilibrium. And if you put this into betting odds and just look at the bets, you can see this. So these are now, I've just taken all the things, the numbers we had from the past slides. So 245 to 1 for their first reaction, 5 to 1, 2300 to 1, 1,000,000 to 1. If you just multiply all those numbers together, what you get is the total betting odds for it going, for a molecule going clockwise versus counterclockwise. And hopefully what you appreciate is that is a big number on the top. It is a 13 billion to 1 odds of going forward versus going backwards. And that's all driven by these 3 reactions, and in particular by these 2 reactions here, 2300 to 1 and 1,000,000 to 1 are really what's driving the reaction forward. So what that means is if we imagine a molecule that has come in, an acetyl-CoA that's come in, odds are that it goes that way. Odds are pretty good it goes that way, but it might not, right? Maybe it goes that way and then it goes backwards, right? There's a 1 in 5 chance that isocitrate goes back to citrate. So maybe it goes there and it kind of wanders around here a little bit. Then it gets alpha ketoglutarate. It's pretty likely it's going to go forward. It's going to go that way. It's almost certainly going to go forward. And then it goes over here. It's going to wander around, right? This is like a random process. It's just sort of walking around. Molecules, we've got succinate being turned into fumarate, fumarate into succinate, succinate back into succinyl-CoA, fumarate to malate, right? The molecules are just kind of bouncing around, wandering around. There's no real directionality, no real favorability there. But then once a molecule ends up by chance after that random walk, that random bouncing around, if it happens to flip over to citrate, it is going to go in this direction, right? And this looks a lot like what a system a physicist would call a Brownian ratchet. A Brownian ratchet is a system like this that has a ratchet in the middle. Hopefully you can see that here. There's this gear that can only proceed in one direction because of this little clip. That's a ratchet. You then put a system like that in randomly bouncing molecules, bouncing ping pong balls in this case. And hopefully what you appreciate is this goes in only one direction. We're basically harnessing this ratchet allows the system to harvest energy from random molecular motion to only go in one direction. This is the chemical equivalent of one of these Brownian ratchets. And so overall, when we talk about the thermodynamic favorability of a reaction or about pathway, this is what we're talking about. We're saying we have a random system. Molecules don't have brains. They're just bouncing around randomly. But because there are certain steps that have a high probability of only going in one direction. We get directionality out of the entire system. Okay, so I said that there are these reactions that are driving the reaction forward. What about those reactions makes them favor going forward? And the answer, it turns out, is the excess NAD plus to NADH ratio. And let me show this with some numbers. So here I've just reproduced the graph I showed before. Zoom in a little bit. It's a 13 billion to 1 favorable reaction because of these favorable steps here, particularly those two on the right. If we ask where does NADH come in, turns out NADH comes in as a reactant at these different positions here. And notice in particular, we have some NADH. Well, it's coming in at 3 points. Now, I didn't really talk about it much before, but on the bottom left of this graph, I have the relative concentrations of NAD plus and NADH in a mitochondria. And hopefully what you appreciate there is there's way more NAD plus than NADH around. That means there's way more reactants than there are products, right? Let's do a thought experiment. What happens if we flip that over? What if we make excess reactants relative to products? What if we flip that ratio? So this is a good point. Turn, think about it, or stop, think about it for a second. Turn to your neighbor if you have a neighbor. What's going to happen if we increase the concentration of NADH? All right, great. Coming back from the pause, what we see is the citric acid cycle actually doesn't run anymore. So what I've done here is I flipped that ratio. Now we have 2.6 millimolar NADH, 0.1 millimolar NAD plus. Plug in all the same numbers before into those delta G equations, and hopefully what you appreciate is that 43 to 1 is much, much, much less favorable than 13 billion to 1, right? So it's much more favorable. It's basically almost doesn't care which direction it goes. And in fact, you can push this further. There are actually some archaea and bacteria that run the citric acid cycle in reverse. We run it to oxidize acetyl-CoA to generate things like NAD+. These guys take NADPH, a close relative of NADH, they oxidize it, and they do that to make acetyl-CoA. So they're using this in a biosynthetic way, and they can do that basically by running this with excess NADPH and excess NADH relative to NAD+, right? This is now a reductive citric acid cycle that lets the system energetically run in the backwards direction. Okay. Another key feature of the citric acid cycle regulation, just to put it in as almost an aside here, is that it's also allosterically regulated. So NADH comes in and it regulates steps that involve NAD, right? So this is an example of product inhibition. The whole citric acid cycle is spitting out a lot of NADH. What this allows cells to do is if you have excess NADH, if that ratio starts to creep up or down, I guess whichever, as this starts to build up, it starts inhibiting its own production. And so that allows the cell to tune the citric acid cycle so that it's only proceeding at a rate where it can keep up with NADH consumption. Okay, so great. We've said the citric acid cycle proceeds in a clockwise direction. We've said it proceeds in a clockwise direction because of this excess NAD plus NADH ratio. Where does all that extra NAD plus come from? Comes from the reduction of oxygen by NADH. So what we have here is NADH goes to NAD plus, molecular oxygen goes to water. This oxidation reaction is extraordinarily favorable, minus 217 kilojoules per mole. This is a reaction that just, it's just in terms of energies, right? That's a covalent bond's worth of energy in this one reaction here. And what that does is it continually drives up the concentration of NAD+, and it drives down the concentration of NADH. So because this reaction is happening, NAD+ is high, and the citric acid cycle can proceed forward. And so if we sort of zoom out and plug all of these reactions together here, we have the reactions of the citric acid cycle, which take acetyl-CoA, turn it into molecular oxygen, and in the process, take 3 NAD pluses and a Q and make 3 NADH and a Q. This is the citric acid cycle. What's happening over here on the other side is these are being oxidized back to their NAD plus and Q forms. They're doing it through the reduction of molecular oxygen to water. And this is actually something that happens through the electron transport chain, which we'll get to in a later video. Okay, and there's the overall reaction, right? We have this oxidation reaction that the citric acid cycle plus the electron transport chain achieve. Key point here is that molecular oxygen is absolutely required for the citric acid cycle to proceed, right? Even though it doesn't appear anywhere in the actual cycle, it is absolutely necessary to keep that NAD plus ratio high, or NAD plus to NADH ratio high, to keep it moving in the forward direction. If you take away all oxygen, the citric acid cycle is not able to proceed. Good example of that is yeast. If you've ever brewed beer, for example, you can grow yeast happily, aerobically. They're sitting there consuming oxygen, consuming sugar. You close them in a tub or a bottle, take away all of their oxygen. What do? Well, they switch over to anaerobic fermentation, making ethanol, because they just can't they can't run the citric acid cycle. Okay, quick summary. That basically we have a large unfavorable step in the citric acid cycle that is overcome by having a huge excess of reactants and depleted products. And that is malate concentrations are very, very high compared to oxaloacetate, which are very, very low, right? So the high malate concentrations and low oxaloacetate concentrations basically let the reaction proceed forward because you've equilibrated the reaction. If we look at the overall directionality of the citric acid cycle, it's driven by this high ratio of NAD plus to NADH. Excess NAD plus, excess reactants drives reactions forward. And this ratio is the result of the NADH oxidation by oxygen, meaning basically that the citric acid cycle requires oxygen to proceed even though it actually doesn't appear anywhere in the description of the reactions. Okay, so hopefully that gives you a better handle on why the citric acid cycle proceeds in the forward and the clockwise direction, not the reverse direction. Next, we're going to talk about how molecules actually get into mitochondria to participate in the citric acid cycle. But for now, I will see you later. Hope that was helpful.